Okay, yes. Good afternoon, everybody. I'm Felix Schmid. On this slide, as it says, I'm the chairman of the railway division, but I'm no longer, I'm the past chair from last year. I'm also a professor emeritus of railway systems engineering at Birmingham, and I do a little bit of consultancy. My interests are in systems thinking, railway traction systems and railway control, and quite a lot in ergonomics and people in systems. So what I'm going to talk about today is about systems engineering and how you should or may want to use it in order to create a useful and usable locomotive for the railway challenge. I've been involved in the railway challenge since its beginning. I think 1 year I wasn't there, and so I can't say anything about that year. But I was mostly there as a troubleshooter, basically helping people find problems, or rather finding solutions to problems, because there always are. And the better prepared you are, the less likely it is that you have got problems. Now, this is a VLife cycle. The VLife cycle has been around probably for about 50 years in different forms. And I have to say that every single academic I know has their own preferred one. This is one which I've used last year with Alex McGrath in Australia, who is the best systems engineer I know. A lot better than me, so I have to say that in advance. And what the VLife cycle does, it divides up your tasks so that you can take them chunk by chunk and hopefully arrive at the end at something which is good and useful. And I think the first thing a lot of people don't think about is that they start with a concept, because if you don't have a outline concept which you're happy with, you're never going to achieve anything sensible. So we'll go down to the next slide. Once you've got this concept, you're doing a big process of taking the system basically apart, understanding the system. So you start with a concept design. In this particular case, you know that you have to build a locomotive, you know something about the track gauge, you know something about the length, the width, etc. And so you've got quite a lot of information, and hopefully your concept design will not infringe any of these constraints which you will find in the documentation. Because if it does, then you will never run your locomotive. So that's wouldn't be such a nice idea. So your concept design is very, very important, and it needs to be something which is feasible. And you then start with the system definition. So what is part of what you're designing? How are you going to apply it? How are you going to use this locomotive? Well, that's fairly clear. You're going to pull a wagon with a judge, with a driver, and you are going to do it along the railway at Stapleford, which most of you will probably have seen by now. So it's important that you grasp all that detail and make sure that you've got it written down in a sensible way. If you have a database, that may be helpful, but I find that paper is quite a good tool, particularly if in the end you have to take it to Stapleford and use it as documentation. Yes, computers are extremely useful in the preparation of things, but when you're actually on site, you might want a lot of documentation on paper. And that's one of my first hints. Don't just rely on computers, because particularly if you want to use the cloud in Stapleford is extremely thick, and you don't necessarily get through to your data because the internet availability, or rather the Wi-Fi ability, anything to do with electronic communications is dire. So you design you find out what you need to know, then you draw up on the basis of that the system requirements of what you have to build. Now you can see green arrows which go from this left-hand side of the V to the right-hand side of the V. Now those arrows mean that if you build something, if you think about something, at some point later on, you will need to be able to validate your design, your construction against this development on the left-hand side. So if you design something which can't be tested, can't be validated, can't be assessed, then when you get to the right-hand side of the V, you have no way of actually stating that you've done what you wanted to do. Very often, validation is referred to as ensuring that you have built the system that you wanted to build and that actually does the job you wanted it to do. Verification, which is the other flow you can see there, verification is about making sure that you have built the system the way you designed it. It doesn't necessarily work because you made the design maybe completely wrong. So you've now understood the requirements. So that will be track gauge, that will be weight. I don't think there's a very strong constraint. That's the wheel profiles. That's the tightest curves, etc. So you need to know a lot about that. Now, your system will have a number of parts or subsystems. So if you decide to have a bogie, then or 2 bogies or 3 bogies or whatever you choose, then you will have to allocate some tasks of your requirements to those elements. So if you have a bogie, then the bogie obviously has to follow the rails. It has to fit the rails, and it has to be able to transmit your traction and braking forces in the right way to the rails, and it shouldn't derail, etc. So you apportion certain things to the bogie. You have things which you apportion to the traction system. If you have an auto stop device, then you will need to allocate that to a particular part of your system. And it's very important that you get the subsystems reasonably well defined, because very often different people do different subsystems, and when you all put it all together, then it needs to work as a whole, of course. So when you've got all these things, then you start doing the detailed design. The detailed design is not yet making things unless you want to build a prototype, but it's about knowing exactly what goes where and how it is made, etc. You then come out of the V into the manufacturing process, and you may well have an additional V in there which deals with a component which you have to develop from the beginning, because very likely you can't buy everything off the shelf somewhere. So when you've actually done that manufacturing side, you need to start to put the system together. And very often on the Railway Challenge, this is the phase where things go beautifully, gloriously, wonderfully wrong, for a number of reasons. One, of course, is if you have spent too much time on the left-hand side of the V, which is, and this is an aside, something which Network Rail and Crossrail and other organizations do regularly. They spend too much time defining what they want and going through many, many iterations, and then running out of time and money when it actually comes to building things. So you manufacture all your components, you buy the components, you make sure that they are the right components, and then you start putting them together. And if you don't have enough time to go through the right-hand side of the V in a sensible way, you have a problem, because basically you will run out of time and you'll end up at Stapleford with 3 boxes of bits and 3 very, very stressed people trying to move these bits into a locomotive chassis, which looks really cool, but it's not the idea. You really want to have time to do the installation properly, to validate the system, to do the safety acceptance, because if you can't show that your system is safe, you will not be able to run it. You then do your commissioning, and that should not happen at Stapleford. I've seen many commissionings which happened at Stapleford, and in general, they did not lead to a winning locomotive. In fact, in some cases, they led to locomotives which were just being assembled and then taken away with a very, very sad face. Then the systems acceptance should happen before, also happen before you go to Stapleford, where you get your chartered engineer to say, yes, this is good, this is according to what you designed, it does satisfy all the requirements. And then, of course, comes the enjoyable bit. You need to maintain the operation over time. Now, I know it's not long, it's maybe 2 months from the point where you have are fairly happy with your system, that it works and it's actually running at Stapleford. Now, and at Stapleford, it has to run for 2 days because there are tests, there are demonstrations, and then there is the run. And the successful locomotive may even be used to haul a train at the end. And that's really glorious when you can do that. It doesn't sound like that is difficult, but it is a real challenge. And so you've got your operation over time, and yes, it's only 2 months, but it's those 2 months where it has to work reliably and safely according to your design. And of course, satisfying the requirements of the competition. And then the final stage is you need to decommission the system, and that's probably something which the next team will do, who will work further on your design. So this is a sort of very brief introduction to the V process. If you follow it, and effectively what you need to do is you need to think about something called a stage gate. So when you go from the system definition and application conditions to the system requirements, the first thing you want to do is you want to say, yes, I have seen everything and I've written it all down. And now I'm going to define this in clear system requirements. What does my system need to do to satisfy those application conditions? And you write those down in great detail with pictures where necessary. And then you don't just jump onto the apportionment, you go back and say, does this actually satisfy all the things I've found out in the first stage or first phase of the VLife cycle on the left? And if you're satisfied you've done that, only then do you go to the next stage. And it's important that your team actually follows that your team follows the thinking and make sure that everybody is happy to go to the next stage, because if you go back later on, you lose time, you lose money, and you lose your impetus to get things done. So that is very, very important. Now I'm going to show a few pictures of some of the years in the past to just show you some of the sort of things which are relevant. This is a two-axle locomotive which has got a hydrogen fuel cell on it, and of course a hydrogen cylinder. And you can see there's some very nicely designed bits here. So let me just get the cursor. So the electronics have obviously been packaged very well. The electronics here. If you look at this side of things, that does not look very structured, very well designed. There's bits which do different jobs here. For example, the emergency relay, the drive control panel, and then some further electrical equipment here. I think the battery is somewhere here, and one of the inverters. So this was a very interesting design, but what you sort of see is that the time obviously ran out, and it was not the most successful locomotive. It did run in the end, but it was quite tight. Now, what do we see here? Well, there's one of the things which you have to provide, which is equipment to lift the locomotive so that you can maintain the wheel sets or the axle or whatever, or the bogie. Now, here it is actually not used for that purpose. It's used for re-railing the locomotive. And what we find every year is that 1 or 2 locomotives either derail at points or they derail in an area where the track is a bit different. And so I have to say, you need to be very careful that you test your running gear very, very well and that you design it properly. You can go out to a supplier and say, can I have some bogies for a locomotive? And this is the specification. You may get what you want, but you really need to understand what the bogie needs to do. If the bogie doesn't rotate freely, then you may get problems. If your bogie is too loose and does not provide lateral stability, then your train, or locomotive rather, will oscillate, it will go sideways, and it will almost certainly derail. So here it had derailed. The area where we are standing is, you've probably seen it, is near the what's called the Haven, and it's a classical area for derailments. Now there are obviously some other problems on this locomotive, and there is the judge, Louise Shaw, is inspecting what people are doing and trying to get the locomotive to work. What they're doing in this particular case is putting the lifting gear back into the locomotive. The person on the right is fiddling around with the chain drive. If you have chosen to do a chain drive for your locomotive as part of your concept, be very, very careful. Chain drives have a very great tendency, the chains come off or the chains break. So they are easy to use, but they are difficult to integrate into a system in a good way. So I think in this particular case, they're just taking the casing off because there is a problem with the chain. And if you don't have a spare chain or 2 spare chains and something goes wrong, oops. And that's an important point, spare parts. The biggest failures we see every year is the power equipment going down. The electric drives are relatively delicate devices, and therefore if you get a short circuit or anything like that, then you lose a drive and you're basically stuck in the middle of nowhere, desperately trying to find a replacement. You won't. You need to have a spare drive board, or ideally 2 drive boards if you use 2 bogies, because you will blow it up. Sorry, it's just essential. Now, on the left-hand side, some very nicely connected batteries. Now, the locomotive, which you're seeing here in the middle, that locomotive is one of those which arrived in 2 boxes with bits and the chassis, which was half assembled. Now, the 3 people who came with the locomotive had done an enormously good job beforehand, but they simply did not have the resources at the time to do it better. So we assembled it, and I have to say we, because I helped quite a lot. We assembled it at Stapleford, and on the Sunday, at the last possible moment, the locomotive actually did do a circuit. It blew up one of the drives, so it could only take 1 passenger because the 1 drive which was left didn't work. Well, there was not enough to pull a properly loaded wagon. So that I really was pleased that they got it to work at the end, but it was very disappointing for the people involved because they had really pushed themselves very hard. Another little example of putting things away. If you have to take off too many things in order to store your lifting gear, that can be a nightmare as part of your project, because you will need to do that when you do the maintenance task. Now this is quite a nice locomotive, and you can see here this is the I think this is the brake gear. They had chosen proper air brakes, and a lot of the equipment is nicely installed. So here is a compressor, I think, and properly sorted out. And this sort of electronic section, it's not brilliant, and there's an extra lid here which obviously didn't fit. So make sure that you've got enough space to do things, and then think very carefully about how you lay it out. And when the last components come in and they are connected with loose wires like this, well, the risk of it not working properly is very, very great, because these are delicate wires, and you can see some delicate wires down here. So make sure that you have got a good plan for installing things in a way that is sensible. Yes. Do I have to say anything about this? It's very difficult to get access to your electronics, and looking for a wire in here is a challenge, and a challenge which I don't relish. So labeling wires and putting them into a nice in cable layouts is a very good idea, because you will know, you will be able to find things. Your cable plans should be available in paper form so that you can track things through the system. Computers are beautiful, and you will prepare them on the computers, but when you're actually doing the work on site, paper makes life so much better. Take a logbook along so that you can take your previous notes. Don't forget those things. And don't just put something like this together. It's not right. This is what it should look like. And that's a really nicely arranged one side of one of the locomotives. This worked very well. I think it was a battery design. I can't remember whose it was. That's the other side of the same locomotive, and you can see it's really, really nicely laid out, neatly laid out. There's no cables hanging all over the place. It's just good. That's what I want to see in June, July. Okay, so that's my take on systems thinking, systems engineering, and ending up with something which works. The things which blow up most often are rectifiers when you short circuit them, and the inverters which most locomotives have these days. The other thing which I wanted to mention right at the end is that the energy recovering, but I think I'll do that after the first set of questions. Okay, Stuart, should we have a short question session, and then I go back to talking about the energy recovery challenge?
Sure. Yeah. So, oh, I got a bit of echo there. Anyway, all those people on the call, if you've got questions, you can either unmute yourself or type them in for Felix. Or observations, comments. I think we also got some. We've got some people from the committee on the call as well. So if they want to chip in with, you know, we've all seen a lot of locomotives over the years, seen what's done well and what's worked well and what hasn't worked well. So we can give you our tips. I mean, I think the thing to remember is we're aiming to get we want everyone to be successful and run reliable locomotives. That's the aim, and then secondary aim is a competition between you all. But the most satisfying thing is turning up and having a functioning locomotive. So any questions from those on the call?
Well, I have a question to the people on the call. How many of you are planning to use a battery locomotive, electrically driven? So let me just, I can't see. There's a lot of the 13 people. So
yeah, I can see.
So that looks like
there's 7 hands, aren't there? 8.
Yes. So I think there's probably more than that. 8, is it? Yeah, 8 hands. Yes. So you can take your hands down again. So is anybody planning to use a generator, a petrol generator on the locomotive?
Yeah, there's one person in the comments that said they're using a petrol engine.
And are you a direct drive from the petrol engine or going through a generator?
No, we go into a generator and then 3-phase power to motor drives.
And do you have a batteries or supercapacitors in between?
Not in between. The supercapacitors are a separate system.
So, but presumably you use the regenerated energy goes into a supercapacitor.
Yeah. So it's a separate bus for the drive, though. It's not in between the generator and the drives.
Okay, yeah. And is anybody else using supercapacitors? Hands up, please. Okay. So that's 4, I think, 4 hands. Yeah. Okay. So thank you very much. The energy storage challenge is something which is fairly horrendous. Fairly horrendous, not in terms of making it work, but it's very, very difficult to actually assess that you've actually recovered energy before you start using it. When we first did this challenge, supercapacitors were very, very expensive. And the people who use supercapacitors to store energy could just about afford a supercapacitor which was just about big enough to take the braking energy in order to then release it for running. Now, what does that mean? Well, it means that if your supercapacitor is just big enough, then it means that its voltage will go up as a function of the energy which you put in, and it is quite easy to measure because it's quite a big change. If you have, because supercapacitors have become cheaper, I've observed bigger and bigger, or rather higher capacity supercapacitors on the locomotives every year. Now, what happens? Well, you put an amount of charge into a huge supercapacitor, and what happens to the voltage? It bloody doesn't go up because it's tiny. Well, the charge produces a tiny voltage on a big supercapacitor. That means that measuring it is difficult, and also because your change in voltage is so small, driving your locomotive is very difficult. So it's a warning. Don't think just because you can using a big supercapacitor is a good idea. Use the supercapacitor which is big enough for the job. Calculate your stored energy in the locomotive and in the trailer, and maybe in 2 trailers if you are very ambitious, and make the supercapacitor no bigger than that. Now, you will have to demonstrate to your judge that your supercapacitor is empty before you start. So that's going to be a challenge of its own. Or you can demonstrate that you're not going, so if you have a charge on the supercapacitor before starting to brake, you need to be able to demonstrate with a very accurate voltage measurement that you're only going back down to the voltage when you are the original voltage when you start to motor. So that's not easy, I can assure you, and you need to think carefully about it. We once had a locomotive which traveled a huge distance during braking, and nobody could demonstrate that this would work, that this was correct or fair or anything else. As I saw the question, and so that's one aspect. If you're using a battery, then you have to measure the energy which goes into the battery and the energy which comes out of the battery, and you have to measure it in a way which is transparent to the judge. And most of our judges have got a very simple view of electricity. It's a magical thing and it doesn't work. Well, that doesn't work. So it's a very important point. And when you charge a battery, the battery voltage will not go up. You will not be able to detect that. You really have to measure the current going into the battery and the voltage at that time. Of course, there's also the internal resistance of the battery and things like that. Now, we've bought a energy measuring system from a supplier in Canada, which basically uses a Hall effect device to look at the current, and it uses a fairly precision voltage measurement to calculate the energy. Yes, energy management is also a solution for very large supercapacitor designs, Malcolm, but I still don't think it's a good idea to go for a huge supercapacitor. It doesn't bring you what you think it does. So let me just see what questions there have been in the comments. I'd ask for advice on energy counters. Yes, once we have got the counter, sorry?
Can I explain what I mean?
Yes.
Good morning, it's Rob Davidson from Newcastle University. Once upon a time, a British Rail. We found a number of solar energy counters used for counting the kilowatt hours into solar batteries and things. Now, our understanding is these are probably the cheapest version we can find, because some do it with a Hall effect, some do it with a shunt. Yeah. But obviously we need a relay that when it's counting down again, it actually switches the traction current off when it gets to zero. Yeah. So would that sort of thing be acceptable?
That would be very acceptable. Now, I think if you decide to go that way, we will probably still put our own energy meter on it. But I mean, it would even be acceptable to just switch off power when the energy meter shows zero.
Yeah.
You don't need to put in an automatic system. It's better if you have, but it's not essential.
Right. We actually don't want to switch off power, but we want to switch off torque. Okay. To keep our controllers happy.
Well, normally you would have yeah, you just ramp back the ramp back the engine. That's fine. Yeah. It's as long as you ramp it back quickly.
Yes, we will.
Okay. So
thank you.
So we haven't yet got the device. I ordered it a little bit late, so I'm hoping it will come in the next 2 weeks or so, and then it will be tested by somebody competent, which is not me because I don't have time. So Brennan, you want to say something about your design? Brennan, Luke?
Yeah, it was more just to check that it's okay to measure current as well as voltage, just as a kind of secondary source of proof of energy transfer.
Yes, I mean, what are you going to use?
Probably a shunt resistor.
No, what are you going to use in terms of energy storage?
Oh, supercapacitors.
Yes, okay. So you definitely have to measure the voltage, but I hope you're not going to use a big supercapacitor. Not going to use a huge one because it simply will cause you problems.
Okay, all right.
When if it's 1.5 times the braking energy which you expect, then that would probably be ample.
Yeah. Thank you.
Okay. Or maybe 2 if you want to be generous. Anybody else for questions, abuse, whatever?
Felix, this is a silly question. When we're breaking the loco, we're also breaking the wagon and judge, aren't we?
Yes, there is no separate braking system.
Yeah.
There's an emergency brake system on the wagon, which is operated by. So you've got 3 people on the wagon. You've got the driver. You've got the running judge.
Yeah.
And the driver, you can probably determine the mass. The running judge is probably about 90 kilos, unless it's Louise, and then it's under 60. Then there's a volunteer from the railway who is the guard, and I can confidently predict that it can be up to 120 kilos.
Cool.
So,
thank you. And the wagon, I gather, is about 400 kilos.
Yes.
Yeah,
So you've got, that's what you have to break.
Yeah.
And if you want to pull 2 wagons later on, then you may want to put that into your calculations.
Thank you.
And I mean, when you come down the hill, you may actually want to brake electrically, because most people will have an air brake or a spring release, sorry, a spring apply and magnetically released brake. So those are not very controllable. Well, they're not controllable really. Okay, no other questions? And I think just the main, biggest and the most important point is your wiring diagram has to be up to date, and the wires have to be labeled according to your diagram, because otherwise the only way I can describe your situation is a deep pool of something brown and horrible, and with your head barely sticking out, and the stress levels getting to the point where you beat each other up. It's a bit exaggerated, but not very much. And judges like to see well-organized wires. Now, that doesn't mean that they are tied together, because that makes it more difficult to move them around if anything goes wrong, but have them nicely arranged and long enough so that they are not under tension, for example, when the bogie moves up and down. Okay. Thank you very much. And if people who are listening to this afterwards need more information, then please send an email and we'll try and deal with it. So I'll put that in the chat just in case. Okay. Malcolm, would you like to say something from your experience And who else of the judges is here?
I was going to. I was simply reacting to your comment that the judges see electricity as one of these strange things that shouldn't work but does. I think we're a little bit more sophisticated than that, but perhaps not much.
Well, I'm one of the judges is very close to me, and she definitely thinks electricity is black magic.
Yes, certainly my analogy of the supercapacitor issue that you mentioned earlier was a bit like measuring an extra litre of water in a bathtub with a ruler.
Yeah. Yes. And
it also helps that the ripples don't settle all that quickly either.
Yes, indeed. Okay. Have we got another judge here?
Yeah, myself, Felix, Rashid.
Yes.
So I think because I've been judging the energy one for a couple of years, and you've probably said it all, so there's nothing to add, really. But I think one of the challenges is to see that after the point which you have in the specification and the rules, that the locomotive runs on the recovered energy. That has been a challenge team after team after team, with the risk of getting disqualified and for that particular challenge. And that's the challenge. So some locomotives have gone a long way defying the normal engineering principles, and then we found that things were sort of, what's the word I can use, going from one system to the other system rather than clear-cut to energy recovery. And that's why Felix's meter coming in, or the device coming in, is very important. And I'm not as clear on electrical energy and the finite decisions. So I'm more on the black art side. So I'll be very honest with Felix, but that helps because I'm looking for clear-cut measurement. Are you using recovery energy? Otherwise, you won't get past that energy judging. So just a comment. Be clear on that yourselves. Otherwise, we will be looking at it from the meter. And if it's all clear, there you go. We'll see how many meters you go.
The big problem is where you use the same battery for the regen energy, and effectively it's the best way to do it because that's the way you would do it in reality. But it makes it very difficult to show what you have actually done. And then like Dave, is it Robert Davidson?
Yes, it's not normally called Rob. I'm not entirely sure what the students call me.
Oh, okay. Anyway, so if you can actually knock out the relay when the voltage, or rather the battery charge, drops sufficiently, then that would be fantastic.
Yeah, that's what we're aiming at. It's made slightly more difficult because we have two independent power systems. We're building a loco in two halves because the room that we're building it in is on the second floor of our building. So it has to go down in a lift. Therefore, we have two isolated systems and we will have two energy counters.
Yes, there's one important point which might be useful for that. And also for anybody who's got two drive systems, which is quite common, don't try to produce the same speed with both systems. Give a torque demand. Yep. Because if you try to give a speed demand to the two systems, then one of them will think, oh, we're going too fast, I need to brake. And the other thinks, oh, we're going too slow, I need to put more power in. And so instead of doing anything, the two systems fight each other. Yep. One tries to brake and the other one tries to go fast. So very important to use torque, or rather force demand rather than speed.
Yep.
Okay.
Thankfully we are. I'll just be happy if they both go in the same direction.
Yes, well, that's an interesting point because when I was in my very early days as a traction engineer, we were building locomotives for an American mine that previously used locomotives from Ericsson's. in Sweden, and Ericsson said the locomotives are all fully tested when they go on site. And the second locomotive they put on the rails had the motors turning like that. And that actually gave GEC the opportunity of selling locomotives to the company, because they didn't trust Ericsson anymore. Okay, thank you very much. I'll hang around for a while and see whether there's any other questions. And Stuart is now probably going to take over.
Yeah, I just thought, would people like to have a few minutes if they want to go and get a drink or have a break? What time is it now? It's 53. So let's have a break till 1 o'clock, and then I'll get going then, because.
I'm sorry I've been so long, Stuart.
No, we got 2 hours, so we're splitting it like equally then. That's fine.
Okay.
Right, so I'll get going at 1300 if people want to get a drink. Hello then, welcome back everyone. Hope it's 1 o'clock now. So I'm going to be talking now for the next 15-20 minutes. I've got some slides to go through. Felix has given a very good introduction to sort of the things to concern yourself about, and I'm really kind of just following on that, looking at the sort of things that you should be focusing on in order to get a successful locomotive. So I've got some slides that are going to come up in a bit. I think my we started doing this event, which where the judges would sort of give you hints and tips a few years ago, and I think for me and probably the other judges, the motivation was that so some years we'd gone to the challenge and quite a few locomotives didn't really work out of the box, and that's not ideal. What we really want is all of you to come along to the challenge, unload your vehicles, and then sit there enjoying the sunshine, because it's normally nice weather at that time of year, and you get on along with the competition. It's frustrating if you arrive having done huge amount of work up until that point, and then try and build and assemble the locomotive on site, because you'll be doing that in full glare of quite a lot of people, and it's stressful, and then might more than likely end up with the locomotive not working that well, and you'll go away exhausted and probably not have got the most out of the competition. But some years I remember teams that ended up winning, they kind of arrive, unload their locomotive, just switch it on to make sure it's switch on, and then they go and play cricket or something, or go and chill out for the rest of the weekend, turn up, do the competition, and then go home with the trophy having not broken into a sweat. So I'm going to have some reflections on this going through, but I think the key thing, I think that's the most important, which Felix already touched on, is kind of project management, systems engineering, and testing the vehicle. It needs to, if you test it well in advance of the competition and have got hours and hours of it running, then you'll be in a much better position. So project management is essential, and systems engineering is essential to make sure that you've got all those built into the schedule. So I'm going to share my screen, so just bear with me a while to do that. So we'll go to the beginning of this. So hopefully you can see all that. So yeah, my name's Stuart Hilmanson. I'm associate professor in railway traction. So my day job is sort of dealing with the black magic of electrical energy and power, and how you make electricity move things. And we talk a little bit about that in this presentation, is how does that all work? It's all magic. It's not magic, really. You've probably already done quite a lot of thinking about traction systems and how to get your train your locomotive to pull the train, and what's the important equation that you need to worry about, and it's shown there, written out in words, which is your mass, or the effective mass of the train multiplied by acceleration is equal to the resultant force on the train. And you've got the train can apply some traction force, and then there will be a resistance to motion, which is caused by all the drag that's acting on the train, like the bearings and the aerodynamic drag and so on. But for your trains, those resistance terms are going to be fairly small, to be honest. Perhaps more significant that you need to deal with is to think about the slope. So many of you will have had a chance to see the test site recently, and although the slope doesn't look very steep, actually travelling back up the hill back towards the station is quite a significant traction demand if you want to go at a decent speed up there. So in that equation, slope is a lot bigger than the resistance term when you're going up the hill. So that's going to dominate your calculations for going up the hill. Oh, that's gone the wrong way. So sort of thing in terms of like calculating the installed power that's required inside your vehicle. So key thing is how heavy it is, what the mass of the vehicle and the locomotive and trailing loads. What is the required acceleration, and all of these things are kind of defined for you. So just go through a process to work it all out. What's the maximum slope? Crucially, what is the available adhesion? What do we think we can get between the train, the locomotive, and the track? And that's an important calculation, because you want to make your locomotive as light as possible. Really, so making a lightweight one is sensible thing to do, but if it gets too light, then it's not going to have enough mass above the driven wheel set to be able to pull the trailing load up the hill. So the trailing load's fixed and defined for you, and you remember it's going to carry a judge, your driver, and the brake person. So they plus the mass of that don't have any traction beneath them. So you have to be able to pull that much up the hill, and that effectively defines the minimum mass of the vehicle that you can do. You could quite easily build a vehicle that was super lightweight, and then as soon as it gets to the hill, the wheels would just spin. Even if it had enough power to get up the hill, it wouldn't be able to go up the hill. So all those things above can be used to work out how much tractive force is required and how much power is required to run your train. And as I said, like many of you are well into your design now, so hopefully you've gone through all these things and come up with sensible numbers. And the answers that you should be getting is in the kilowatts range. So probably like 2 kilowatts is at the lower end, and like 10 kilowatts is at the upper end of what you'll end up installing in your trains. If you're well below that or well above that, maybe something's gone wrong. In your traction drive, you obviously have got energy losses, and the energy that goes into your train has to be accounted for. So we've got your traction energy that comes in. Some of it is lost in the converters, some of it lost in the motion of the rail vehicle. So there's nothing much you can do about that. And then potential energy loss. So if you're going up and down the hills, that can be positive and negative. And then traction energy predominantly goes into sort of kinetic energy of your vehicle, and then you'll get some back in terms of regen braking energy. So those of you who've got like battery systems, then it makes sense to have a regenerative system that's operating all the time, and that'll give you your best, the best type of vehicle. So when you come down the hill, the best way of braking a train full stop really is to use electric motors, and this is how it's done in real railways. We often, if we're designing high performance kind of metro railways, you really want to design your traction system to do as much of the braking as possible, so you minimize kind of friction braking. So if you've got a train that has brake discs on it and you don't hardly ever use them apart from parking, that's kind of the best situation that you can have. These are some equations that dominate everything here. So we've got force is mass times acceleration, and then the force that you get due to gravity going up the hill is mg sine alpha. And those of you who will have fiddled around with these equations will know that sine alpha for small angles is the same as alpha. And I can't quite remember what the gradient is, but somebody, maybe one of the judges, can put the gradient in the chat. I think it's 1 in 60 or something like that. I've forgotten now. And then you can use, in order to work out the power that's required, you can do force times velocity, and as I said earlier, the power that you require for your vehicle is kind of dominated by how fast you want to go up the hill. So in that equation, power is force times velocity. You can just get the force from gravity and multiply it by how fast that you want to go up the hill. And if you put it in meters per second and newtons, you'll get the answer in watts. And as I said earlier, the power that we're looking at is in the range of sort of a few kilowatts is the actual traction power that you need to get up the hill. And if you want to make it look really complicated, you can write that down in terms of differential equation of motion, but you don't really need to. I'm just showing that there to make it look more complicated. And there's some pictures of trains. So it's important to your trains look good. This is well, obviously you can read, that's Amtrak, so Sealer train running in the States. I'm just showing you train pictures because we like trains, don't we? This one I think is one of the most attractive looking trains. It's a 500 series Shinkansen, West Japan Railway Company. This is one of my favorite UK trains. Sort of joking a bit there.
No.
This is a pacer, but there's some really interesting things about this train, because if you look, it has got it's only got two wheel sets per vehicle. So I'm kind of showing you, it's a bit of a joke showing you it. So that train's got bogies on it, and that train's got a single wheel set. And those of you who've ridden those trains will know that their ride comfort isn't that great. So if you're concerned about ride comfort, then, which you might be, then the best way of doing it is through a bogie, because you get a geometrical sort of filtering of the track, and of 2 stages of suspension. So a bogied vehicle is always going to give you a better ride quality than this one. And then there's one of our modernish trains. That's an IET train, one of the Hitachi Class 800 train sets. I think it's a Class 800 anyway. Right. And then Pendolino. This train is one that I used to ride a lot more before coronavirus, running down from Birmingham to London West Coast Main Line, from Glasgow and Edinburgh and so on. I'm showing you this picture. One of the things I wanted to say about it is, I remember a couple of years ago, me and a colleague were talking about this train in front of our engineering students in University of Birmingham, and my colleague said, "Oh, this is one of our newer trains," and then I which it is, because it's kind of half of the way through its life now. But then I pointed out that it's probably the same age as most of our students. So these trains are kind of around about 20 years old, or somewhere around that. But they've already been around for a long time, but they still look good and they're still doing a good job. So I think that's one of the things about railway vehicles, is they have very long life, and they can provide, they do an awful lot during that time, which is quite phenomenal, really. And this is one of the vehicles. Actually, Felix showed some pictures of this vehicle in his presentation. Here it's running, I think, probably at the end of the competition, because we've got more than one judge in there. So you often get a chance to run the vehicle at the end, or at other times whenever your team can get a bit of a pleasure trip in the vehicle too. So there's no other reason for making sure it works when you turn up. So I'm going to talk a little bit about the motors that you might have on your train. So pretty much, I don't think there's been any that haven't had traction motors on over the years. Maybe they have, but pretty much everyone decides to use some sort of motor to drive your train. And there are kind of three classes of motor that you might be considering. An induction motor, which is an alternating current motor, a direct current brushed motor, and then a direct current brushless motor as well. And there's different, depending on your understanding of electrical engineering and control, you might pick different one. If you're new to electrical engineering, then probably the safest option is going for a sort of DC brushed option, but that's not necessarily the best thing, because there's some downside. It's often easier to get a brushed motor working and controlled to some extent, but it doesn't, there's some downsides too. How do we produce torque from a magnetic field? I'm going to just mention this a little bit. So that's a picture of a motor, and we've got a bit that's called stator, and then if you look at inside an electric machine, you've got a magnetic field, and it's shown here using magnetic field lines with north and south pole. One thing that's interesting about electric motors, I think, is the magnetic field inside the motor is really, really strong. You go up to as much as you can be supported by the material, which I think is around about 2 Tesla or thereabouts. And there's no magnetic field that leaks outside the machine, or very little of it leaks outside. So things don't suddenly start sticking to your traction motor, because all the field is contained inside of it. An alternating current machine will have a field in it that looks a bit like that, and actually, if you could see the field, it rotates. So we have what's called a rotating field inside the machine, with the north and south pole running around the circumference. In a DC machine, if you were to be able to see the magnetic field inside the machine, you'd see that it's actually stationary. It doesn't rotate in the same way, but you still get rotation through sort of the Lorentz force, which causes forces on the conductors. I think that's the other thing to say is in both sets of machines, you have conductors, bits of wire, either aluminium like conductor bars or bits of copper, that are sitting inside electric machines, and they have currents that go through them. They get induced voltages across them, and they are in a magnetic field. So if you remember all of those funny left and right hand rules, that's the things that govern the how the machine works. Basically, you've got current flowing in conductors that have got the current flows in a conductor inside the machine, and has that conductor is inside a magnetic field, and then you'll get a force that's kind of the cross product of those two. So 90 degrees from both of those vectors, you get a force developed, and then the thing tends to rotate. If you're doing an AC motor, which some of you might be, then you'll be needing to generate a 3-phase supply on board your vehicle. If you're you can potentially have this at quite high voltage. So if you've got electrical engineers in your team, then you might actually have like an industrial drive that on your vehicle running at 415 volt 3-phase supply that's running your traction system. So if you're doing that, that's kind of dangerous level of voltages. So you need to make sure you're doing everything properly and have got all the right protection on everything. So yeah, once you use, so that's what I said earlier. If you've got electrical engineering in your teams, then this is a good way of doing it. However, it's a bit more complicated, and you need to know what you're doing. You can't make it up as you're going along. You can't wing it really with a three-phase system. However, the motors for three-phase system, are cheap and cheerful, and robust and unlikely to go wrong. So they're potentially a very good way of driving your train. And in fact, that's how most modern trains are driven, with an AC machine. This is just sort of a standard industrial motor shown here, but traction motors on board trains are pretty similar to some extent. There will always be some differences, but they're very, very robust and last a long time. A direct current machine is simpler to some extent in terms of like running it, because instead of having to make three-phase AC, you just have to have a variable voltage DC. So you can have the simplest way of driving a motor is getting a battery and a variable resistor, and then connecting the variable resistor sort of in series with the motor, and that would give you like a series controlled type of traction system, which is the same type of traction that's currently used. And I believe that we haven't upgraded Bakerloo and Piccadilly lines yet, but if you want to go on a train with a DC traction motor, those are the trains to go on, and they're controlled by varying a resistance, putting a resistance in series with your motor. So when you're going slowly, you have a big resistance, and then as the train accelerates, you change the value of the resistance to get the train to go faster. So this is a sort of circuit diagram of a DC machine, where and you'll get these slides afterwards, so I won't go through it in detail now, but you basically need to have a variable voltage supply to control your traction motor. This is something that'd be quite interesting. If I was doing this project now, I'd be thinking maybe we can use brushless DC machines. I know you can get quite powerful little motors that are used for things like remote control cars that are nearly the right kind of power level for what you want to do here. So yeah, like I said, if I was 20 years younger running this project, I'd be thinking maybe can we do something clever with this. One of the interesting things about some of these motors is they spin really fast, so you can get motors that spin nearly 100,000 RPM or something crazy like that, or 50,000 RPM. That how do you connect that to your wheel set? That's like the electrical engineers could say, yeah, here's your motor, here's the power, and it's got a shaft that spins at 50,000 RPM. How are you going to connect that to your wheels that don't go very many revs per minute? But there, so that's what I think about. So ideas from the web. There's a company called IMechE Motors. You may have come across. Lots of students and teams have used IMechE Motors over the years. We've published a paper on the train Hydrogen Pioneer, which is published in the IMechE's proceedings, part F, which is the Journal of Rail and Rapid Transit. So there's a link there that you can find it. And then remote control kind of car supplies, they've got loads of stuff, and then at the bottom there, the web link is Robotech, which has links to motor controllers. So there's a huge amount of information on that site that tell you how to run motors. So I hope maybe a lot of you have done all this, done some energy calculations and vehicle simulations, or already worked out the power demand. Things you need to buy then are motors, motor controllers, and something to control the motor controller. So your motor controller generates the right voltages and currents for whatever motor you've got, but then you need to tell your motor controller, you know, what torque you're after or what speed you're after from the motor. So there's something to control that, and that might just be the most simple thing, might be a potentiometer, but then equally you might have some sort of CAN bus or Ethernet interface or USB interface. There's a whole host of ways of controlling motor controllers as well. Felix has kind of touched on a lot of these things. Sort of the common problems that we get here, and these are focused on electrical problems, but the first one is like mixing power circuits with electronics. So what we mean here is you need to think about like all of the sort of electrical noise that might be happening inside your train. So you've got you know, your traction motor, traction motors, or your DC motor that's connected to a motor controller, but then you might have some sort of common earth with your electronics. What you don't want to have happening is the noise that's produced by your traction motor then interfering with electronics. So somebody needs to give that some thought. It's really important, and my teams, or the teams at the University of Birmingham, have had problems with this over the years, and it's surprisingly common. Blowing up the motor controller. So the motor controller, you know, is designed, it can deliver quite a lot of power, etc. And it's quite easy to kind of end up with problems with your motor controllers because you haven't set them up properly, and you end up blowing something up in it, and you usually from overcurrent or something. Equally, blowing up electronics is common, and even I don't know if we might have even had people like blowing up motors. And something I mentioned already, getting the traction to the wheel set is a very, very difficult problem. So you know, the wheel set is moving in 6 degrees of freedom pretty much compared to where your motor is probably housed. So having a flexible coupling between the motor and the wheel set with the right amount of reduction between the motor speed and the wheel set is not an insignificant problem. And Felix has already mentioned, you know, doing this is not that straightforward. So think about that. The temptation is to use a chain drive, but there's a reason why we don't see many chain drives on real traction trains. Is because they're rubbish, and they don't last very long. So if you look at a real train, there's some really clever ways of getting traction to the wheel set, and should borrow those ideas with pride and adapt them. There's also other systems where you can think about, you know, looking at drive systems for cars, like the universal joint that runs a front wheel on a car. You might be able to kind of hijack that, and you know, buy parts like that already have like transverse drives in them, and so on. So getting traction to the wheel set is common. And another thing that's important is understanding about what needs to be earthed together. So the electrical engineer in your team, you have to think about this to make sure it's done properly. We have seen over the years, you know, cables kind of catching on fire because there's some fault in something, and instead of the current, you know, you may have like 90 or 100 amps or more going through what you think is going through your motor. If it doesn't go through your motor and it ends up going through another part of your train, it's got potential to melt stuff, and that sort of things happened before. You need to think about what happens when you do an e-stop. So this is a big challenge for any system where you need to do any sort of emergency stop. What you have to think about what happens to energy in the system when an e-stop is activated. If you have an e-stop which like open circuit breakers, then you have to think about the sort of microseconds when things are stopped, because it's quite easy to generate enormous voltages when you stop large currents, which is what you might be doing. And there's also mechanical energy in the system that needs to go somewhere as well. So quite often, if the e-stop's not designed properly, your first time you hit it, you might stop your train, but then you'd also damage a load of other stuff because you've created a massive voltage somewhere that only lasts a tiny, few microseconds, but it's enough to do some damage on stuff. More thing to worry about, I think, is a mechanical engineering challenge, but I think most of the problems that we see certainly on the test days are electrical and systems engineering issues. Felix was already mentioned about having understanding your wiring diagrams. So we do that in Real Railway by having identification features of where each cable has a label on it at each end. So if you're trying to do fault finding, you can look at the cable and say, yeah, that's cable X543 or something. Crimping and terminals. If you've got somebody who's competent in crimping, then get them, pay them a lot of money. It's really important to make sure your connections are done properly. Your things will be wiggling about, so you don't want stuff coming loose, because it can be really time consuming to find out what's loose. So things like cable schedule. Things need to be protected with fuses as well. I've already mentioned earthing and how to do that properly. Some of my sort of insights: you cannot win the project or be successful in it if you don't have proper project management, and you cannot win unless you do all the paperwork. So these project management and paperwork might seem kind of the less interesting part of the projects, but they're absolutely essential to getting it working right. And you need to get the right people doing those jobs. I put my hands up and said that I would be not a very good organized project manager, and I'm not that good at paperwork either. So you need to find people in your team that can do that stuff. Testing is vital. So if your train works a month before the test day, then it's probably going to work on the test day. So I would schedule in testing and also doing things like inviting senior people in your organization to come and see the train running. We'll give you that incentive to get it running earlier, and then you reading the manual. Somebody to go through with a fine-tooth comb all of the IMechE docs. You need somebody who's got attention to detail to make sure that you've got all the boxes ticked, because the teams that end up winning are the ones that have done everything well, rather than just nailing one task. It's the ones that have gone through and done good and very good at all the tasks, rather than kind of just nailing one aspect of it. You are human beings, and you're going to have different types of people in your team, and it's important to for your team to work really well together. And you'll have organized people, kind of unorganized people, extroverts, introverts, like natural leaders, followers, and then people that worry. All these people, I think, are vital to successful teams. If you've got a really diverse team, things will be better. But it's important to kind of understand how each of your team members, what their natural kind of tendencies are, and then work within your team towards people's strengths. So an organized person who likes the detail, likes reading, and is very good at reading and remembering stuff, they would be good at terms of helping with the paperwork and the project management. And then you might have more inventive people that that are quite good at coming up with the wacky ideas that then get turned into the real technology and so on. But it's important just to recognize that within your team that you might have all these people, and you need to be respectful of people's sort of natural tendencies to get the best out of them. and try and avoid any conflict then, because things get stressful sometimes. Yeah, wiring like on the right hand side, like, it looks beautiful, doesn't it? That's really nice and neat, and all, huge attention to detail on the right hand side, and then the left hand side is a complete mess. So if your train looks like anything like on the left hand side, and you're trying to find faults, it's going to be a nightmare, and you don't want to be sitting over a mess like that while you've got the judges peering behind you, because the judges will be trying to like help you fix it, and I'm sure they might rather look at something that you've got on the right hand side, which was really nicely neatly laid out with color coding and so on. So that's it for me. I'm going to stop sharing now. I'm here for sort of any questions some nice comments about paces in the chat, but any questions from everyone out there?
I suppose I'll just jump in with something I've said in the chat, Stuart.
Yeah, sure, Ben.
Obviously, we've seen instances beforehand where obviously we've been generous in what we've let try and get running at the weekend, in the interest of trying to make sure that everyone's hard work doesn't go up in smoke. In some cases, literally. But one of the things we have seen quite frequently over the years is that when teams have done their testing, they've done it relatively local to where they are. They've had very little need to basically disassemble to transport and then rebuild to ensure that the locomotive runs. Whereas obviously when you are carting all of your kit up towards Leicestershire or down to Leicestershire, depending on where in the country you are, or even where on the continent you are, you end up in a position where you are having to do some disassembly, reassembly, etc. Some things do not travel very well at all. So I've said this for a few years now. If you're in a position where you know your locomotive works, you would do well if you have the time to disassemble as if you were coming to Leicestershire. Drive around in a van for a couple of hours and take it back to your workshop and rebuild it and check it still works. That will allow you to flush out any gremlins that might otherwise crop up from the journey and mean you're more likely to hit the ground running when you get up to Stapleford.
Yeah, I think that's a really good point, Ben. I think the sheer act of transporting your locomotive, that's not that's a big task in itself, is understanding how to load it into the vehicle that you're going to transport it with, do that safely, and unloading it, and so on and so forth. So if you've done that a few times, you'll get much better at it. It's a big activity, just packing up the vehicle into whatever you're going to transport it in, and the more times you do it, the better you'll get at it, and you as Ben said, you iron out any problems of you're kind of shaking down the vehicle, aren't you, in terms of taking it on and off the transporter.
Quite literally.
Yeah. I don't know what it's saying about your driving though, Ben. Like if you shake stuff to bits.
I was thinking it's more the state of the roads in the country, to be honest.
All right, okay.
Yeah.
All right, fair enough. Yeah, it's a good point. Any other queries, questions? Well, we've got quite a few judges here as well, so feel free to step.
I'd like to ask one, has anybody yet used a Sevcon motor controller or a motor energy motor?
I don't know if I can't remember if anyone's used them before.
Okay.
Rob, but
thank you, Thea.
But maybe, yeah.
They're made local to us, and we have good experience with them on Formula Student.
Okay, good. Yeah. Are you using them then?
Yes, we've actually got, we're a bogie loco. Each axle's driven independently. So we have 4 Sevcon Gen 4 controllers and 4 motors with carbon fiber tooth belts. Okay,
and what are the motors? Are they, what sort of motors?
Well, AC synchronous.
Oh, okay. Is that with the permanent magnet synchronous?
Yes.
Yeah.
Yeah.
Okay. Yeah.
They're the biggest you can get in there.
Okay.
With our brakes are V-belt pulleys. They were the cheapest we could find, stuck on the motor shaft.
Yeah. Okay. Any other questions, comments, observations from guests? No, I think I've looked through the chat. I don't think there's some nice comments about paces. They're well, yeah, they're a novel vehicle for sure. That's okay. Let me just look through. Yeah. Okay. In that case, I'm happy if we draw the session to a close. I hope you found that useful. It'd be available as a recording if you want to look back on anything. I think if I can sort of summarize with my there's some questions on for the new challenge. If you want to ask them, but yeah, but I think just my reflections on the competition is to again emphasize the project management aspect. One of the things I've done in my research career is we worked in partnership with Porterbrook to develop Hydroflex, which is a conversion of a Class 319 to hydrogen fueled train. And the project manager that we had on that was phenomenal. He controlled everything really well and managed a very complicated project and delivered it on time. Interestingly, we have over the years had people with kind of military backgrounds come from Navy or Army or Air Force in our teams, and I have noticed an observation is they've really got good kind of project management skills. Not saying that they're the only people that have project management skills, but if you've got any people that from those backgrounds, they're often really good at getting the job done in time and getting it done good enough, rather than trying to make it a perfect thing. You just go, what's the best way of doing this and meeting the requirements, and once you've done that, then that's the best way. So there's someone called Rob that's got some questions on the new challenge. Do you want to unmute yourself and fire them off?
Yeah, I didn't want to cut you off there.
It's okay, go for it.
So I got some things from the tech spec and from the rulings. I have something about the points. In point B21, they said that the reliability challenge will give us a total of 200 points. But under section C 6.6 in the tech spec, it says that the maximum points are 150. So there are two different maximum points there.
Yeah, that's just a typo. Don't worry, we'll rectify which one that should be, and it'll get uploaded onto the website. Well spotted. Checking if you were looking.
Yeah.
To be clear, it is 200 points. The other one's a typo.
Yeah, then I noticed we got some time cutoffs now in the rulings also for testing purposes, like 10 minutes for the auto stop challenge, 20 minutes cutoff point for ride comfort and so on. So is it clear that you can't just test the auto stop if you want to and run through the other ones for the testing day on Saturday, I presume?
Could you point me at the reference?
It's B4.
I believe this is to do with us introducing a minimum or a maximum time for the challenge runs on the Sunday, and the ability for us to cycle all teams through if everyone is attending and has working locomotives. Obviously, time is a thing. We only have so many hours on the Sunday before we have to pack up and everyone go home. So in that case, previously we've had people keep attempting challenges up to a maximum amount of attempts. We've had people going over time on their slots, which incurs reliability penalties and so on, but also disproportionately impacts the other teams on their loops.
Yeah,
By putting in some time limits, the clock starts when you leave the signal at the station. You have up to 10-minute marker to successfully attempt or fail the auto stop challenge, and then proceed forwards. So it's almost like latest time of arrival at key points to ensure you get round.
The main point that was kicking me off was the part where it says for each of the 3 scheduled locomotive runs. So there's the dynamic testing, there's the testing for our team, and there's the run itself. So that's the 3 runs, I guess.
Again, it's mostly to do with slotting. It's most impactful on the Sunday, but it is to do with the slotting and making sure that all teams get their fair crack at each of the sort of amounts of time you're allowed on the railway yourselves. So it's all linked, because obviously we've got a very tight schedule over the challenge weekend. If you were going out and on your test run, say on the Saturday, you only want to test your auto stop, time has to be given. You can explain that at the time, and those timings would probably be reworked to allow somebody else to come down behind at a certain point, and to make sure you're back in the station and out of the way by the end of your slot. The last thing you want is to be basically struggling with the auto stop, and then you've still got to go around the loop and then back up the hill through the tunnel, etc., to get up to the station.
It's cool. It's about the reliability challenge in itself, right? With the point deductions. So then I've got 2 last ones. It's about the new challenge, the refueling one. So this come in new, and as it's stated in the old rules, we already had a 2-minute maximum time for refueling, and it's still in there. Is it in comparison? So now we have a challenge about it, where we have to be even faster than 2 minutes to refuel our locomotive.
It's not that you need to be faster than 2 minutes. It's more that previously it was taken as given that a locomotive could be refueled in the time specified. Whereas now, looking at how industry is developing, both in the automotive market and in rail and other transport sectors, refueling is key. So we wanted to try and understand how you would go about refueling your locomotives, be that charging them, switching out interchangeable batteries, or however your primary source of fuel for traction
or the hydrogen
undertaken.
Cylinder.
Go on.
Or the hydrogen cylinder, Ben.
Yes, exactly. So it's basically trying to make sure that you are able to do it. And similar to the maintainability challenge, it's a challenge which will be done as safely as possible under a specific method statement that the teams will design themselves. And basically it will be against you're against each other in a competitive environment. Whilst it needs to be quick, and you have requirements in how quick you should be able to do something, sometimes things don't go to plan, and that's fine. And that's just something we're trying to check as part of the challenge.
Yeah, exactly. With this challenge, it was in the ruling. It was in under 4.1 technical requirements in general. There's the point where refueling from 0 to 100% capacity shall take no longer than 120 seconds, and no energy storage asset shall have a mass greater than 25 kilograms.
So that's all true. Yeah.
Yeah, and it is directly referred to in the challenge itself to this point, 2.4.1. So it's still a 2-minute limit for this challenge, and and the 25 kilograms are still right. Okay, nice.
Yes, it is, simply because those the 2 minutes and the 25 kilos are just basic economic and safety limits. So even though there's a challenge, who can do it fastest? We we wouldn't want a loco that it took longer than 2 minutes, because that would be not commercial, and we wouldn't want a removable storage that was heavier than 25, because that wouldn't be you would be very unlikely to write a method statement that we saw as fit for purpose if you had elements heavier than that. It just wouldn't be safe.
Yeah, because in the challenge itself it says that you can build an installment to remove your energy assets. So then if you have an installment, you could basically lift like your energy assets all at once. And if you have 4 batteries, you have to lift them one by one, because one asset is already like 16 kilos. So 2 are 32, and you are over the limit.
Well,
so this was the main.
Yeah. Even with kit, I think we would be worried if people were slinging around 40, 50 kilograms of battery in one big lump, even if you did have a piece of kit to do it. I mean, you're right. It's a good point. If you could convince us, perhaps we should consider something that is heavier. But just on the face of it, until we've had a go and seen what people do, I think we'd be happier not to have anything too heavy flying around. Perhaps you may be right. Perhaps in future years we'll look at something heavier, but instinctively, great big things flying around are not safe. This is why we always get so worried about the loading and unloading. Because this is where we know, this is, as far as we're concerned, almost the main dangerous part of the weekend. Because this is when you're starting to deal with really heavy things being moved, and you want to minimise that. And I would imagine. And don't forget, this is something that is going to happen in real life. And it's happened in the past 100 years as well. Where people keep electrical vehicles moving by just changing the battery packs out and putting a new one in, and that's something that could quite easily happen in the future. And I would imagine they may well consider having it modular, so they just take them out, not the entire thing for a tram or a delivery van, but they just have about 4 or 5 sensibly sized modules that go in and out. We don't know how things will go, but to be honest, I imagine if you did have a ton of battery in a big, urban tram that they kept going by replacing the packs, they'd probably do it not ton at a time, but they'd probably break it down into pieces. But we'll just have a look at how the teams do it over the next few years. So we try and keep things safe. We also try and keep things vaguely relevant, very relevant to real life. And as I said at yesterday's site visit, there's nothing in the spec and there's no challenge that doesn't relate to something in real life. And I have a sneaking suspicion that with very large vehicles, people would be expected to remove the battery packs in separate modules, not just all as one, because I think you'd start to talk about really large bits of kit flying around otherwise.
Thank you.
Could I ask a question about the battery packs? Because it would certainly simplify our design and probably make things safer if we've basically got 4 car batteries in series with a 48-volt system, and it would certainly be much more convenient to move a tray of 4 car batteries horizontally. We're already planning a trolley, so sliding one module out and another module in. And certainly if you took the weight limit of 25 kilos, typically 250 newtons as the force limit, we could easily do it with that. But would it be worthwhile showing you that design, or do you simply want to say no?
Well, for this year, I think we'd better say no, because it'd be unfair on the teams that are already breaking the stuff down.
That's fine.
I completely agree that if teams convince us, and particularly the judges and the people who look at the safety method statements, that safe systems that can deal with heavier weights are possible, then obviously we like to change the tech spec every year. We like to change the rules every year deliberately. And so I think we'd be more than happy with that. Yes, absolutely.
Okay.
And then I think your hand, Tim, is the only thing left at this moment in time. Is that? Do you want to chip in with anything else?
Yes, just say that do remember there are hints and tips slides on the website already about what not to do with chain drives if you really are going to go down that route. You know, be very careful of earthing. Be very careful not to rely on friction connectors because they will come undone in a vibrating train, even if they don't in the lab. You know, don't just ever rely on push fit connectors. Always do the screws up. Always put a Jubilee clip on the pipes. That sort of thing. There is a hints and tips page as well as Simon's slide on the website.
Any more comments, questions? I think it's been a really good discussion. Hopefully you found this whole seminar session useful. Wish everyone good luck in their remaining activities. Any other comments from the judges that and the committee members that are here either? Thanks for stepping in where you have done. Okay, in that case, we'll.
I'd certainly be happy if people wanted to discuss anything. I'd be happy to talk about it, and when we know exactly what the energy meter system looks like, we'll pass on that information.
Yep, thank you, Felix, and thanks for your presentation earlier. So I think that's it then. So have a good afternoon and good weekend, and see you at the competition. Thanks, then.
Thank you all.
Bye bye.
Thank you.